Hello and welcome to our Texas Instruments Australia webinar for today. Today's topic is fun with graphs and your presenter is Peter Fox. I know Peter has got some interesting material for us. With our fun with graphing, we're looking at reflections, translations, dilations, all for a range of different graph types. And of course, involved in that is art as well. You can actually draw some cartoon characters. And I do know that in one of the first activities, Peter is going to ask you to see if you can identify a well-known cartoon character. That's all from me. I suggest we hand back to Peter now. Peter, we can see your screen now, and no, it's not that character there. We know who that character is on your calculator. But I know you've got another one.
Well, hopefully they do.
Yeah.
So some of you that are attending today may have seen the trailer for this webinar and probably wondered how these graphs were done. All of the graphs in this particular one for Mickey Mouse, they were all done as ellipses. They're actually created in parametric mode, and that's because parametric mode allowed me to provide a greater control over the domain in both the X and the Y direction, obviously because you're placing constraints on T, whereas normally we'd be placing them on just the X value. So the image itself might be quite playful, but as you can see, we can easily crank up the level of complexity of the mathematics. You can also crank it up a little bit by requiring students to justify their selection of the domain. And obviously for these ones, I was using things like sine T and cos T and dilations and translations thereof. So that would really crank up the degree of difficulty. So scaffolded as well. So it depends on how much detail you want students to communicate with regards to their derivation of each equation. Also, students can be surprisingly competitive when it comes to the accuracy and level of detail that they include, because I've done this sort of thing with students before. The level of detail amounts to how many different graphs sometimes that the students would do, and that from a teacher's perspective or a learning perspective might be associated with the amount of repetition for that skill or concept. You can let students choose their own characters, for example, and therefore moderate it for easier or harder tasks depending on the student's ability, and even get the students to create a poster with their final result and all the equations that they put into it. So yes, students get quite competitive when you do things like that. So our first question, as Brian mentioned, is to have a look at a mystery cartoon. So what I want you to do is, as soon as you think you know the answer to this mystery cartoon, I want you to put it in the chat. Now the record so far, no pressure, is about 12. So in other words, 12 bits of the puzzle were revealed. There's none on the screen at the moment. Now there is one. Now if anyone can get it from there, I think they've probably cheated. So now we have 2 bits of information on the screen, and I'm just monitoring the chat to see if anyone's thrown an answer in yet. Let's go up to 3 bits of information. Yeah. Looks a little bit like an eyeball, but not necessarily.
Prize is still there for grabs. I reckon I can see it.
That's it. Wow, that's impressive. I think you might know the answer already, though. Now, just in case people are wondering, I've done some circles, I've done a parabola and 2 straight lines.
We have a Peter who reckons it's he's very close. He's on the right track.
Ooh, okay. There's a few more bits in there. Oh, and someone else is, another one's getting really close.
I'm going to give the money, stop the clock.
Oh,
I'm giving the money to, I think
Trish,
it was actually on,
Patricia.
On 8.
Yep. I think Patricia's got it. But let's see if anyone else can catch up to where Patricia's at.
I thought I had Matthew.
Who it is.
I thought Matthew had it. Oh, it's okay.
No,
I don't know my cartoon characters well enough here. I know the show. Right. I think everyone is now saying The Simpsons.
We're out to 15 and see if anyone else can jump in on it. Now, so far, most of this, well, so far all of it is parabolas and straight lines and circles. Don't think anyone else has got it yet, but I'm just going to zoom through it for them. And yes, Patricia was right. It is little Lisa Simpson. Now,
I thought it was Marge.
there's a couple of things. Yeah. Now, Marge has got the bigger, taller hairdo.
Ah, okay.
Whereas Lisa, and Lisa's always got this little bead of a necklace sort of thing with the pearls or whatever it is on it. I guess they're cartoon type pearls. So there's a couple of things happening here. All of these are basically just straight line graphs, and each one has a domain constraint, and there's various ways students can do those domain constraints. They can either do it by trial and error, or another thing you can do is you can just go P and put a point on the screen and get its coordinates and drag it to where you want it, and that way you know your minimum or maximum X value, depending on which line you're drawing. So you can set your domain up by just moving that around, and then when you're finished, just move that off to the side and draw your next straight line, and then drag it to where you want it to start, where you want it to finish, and therefore you've got your, again, minimum, maximum for your X values. Now, what can we do? Say, for example, if you recall back to the days of drawing dot-to-dot pictures, you can pre-populate the screen to fill in the curves. So in other words, if you wanted to do Lisa Simpson and do it at a lower year level where they were only doing straight lines, let's say it was year 9, then just put all the curve parts to it in, and then the kids can just finish off with all the straight lines. It can help if there's a picture in the background, and that's one of the other things we're going to be looking at is how do you actually insert a picture in the background. Or you might put points on the screen. If you want specific results that the kids are going to come up with, a bit like a dot-to-dot, you could write them as coordinates and get the kids to fill in the equations that way. So it's a very versatile activity. Personally, I prefer the one where the kids actually use their own cartoon character, but it does preclude the fact that there might be some curves in there, which will be difficult. All right, so that's that one. And let's go on to the next one. Putting pictures in. We can use it for more than just cartoon characters. So have a look around at where pictures might be meaningful. I know we've seen some where you might have, say, the Harbour Bridge or something like that, and we want to graph a parabola, or you might have the Opera House and look at the circles, or you might have a Golden Arch, for example, and then try and map a curve to that. This one, on the other hand, is quite applicable to, let's say, students in Year 9 where they're starting off with things like gradient. So you can present the students with this picture, or you can put it in the background, and I'm going to show people how you insert a picture in the background. And of course, what could we do with this one? Well, obviously we're looking at the slope of this ramp, and we know what the ramp's for. It's a wheelchair access ramp. And the general code for it is that it's a slope as 1:12, so it's given as a ratio. So we need to move from ratio to gradient or slope as we know it in maths. Now, the beauty of doing something like this is when you put that picture in the background in your calculator, then you can get the kids to actually graph it and see, does it actually meet the code? Is this slope more than 1:12? Is it steeper than what it's supposed to be? And there's usually plenty of access ramps around the school. And not saying that kids take their mobile phones to school, but I suspect a lot of them do. They can certainly take photos, and then you can transfer that to the background image. So let's see how that's done. Let me just go back to the calculator. I'll start a new document, and I'll put a graph in. You can't put a picture in the back of a calculator application, but you can for graphs and geometry, and even notes you can put pictures in. Now, you can only do this directly on the software, of course. Now, the students get the software when they get the calculator, so they can do it. Or if you're doing it for a whole class, you create the document and send it to the kids. Or if it's an activity on our website, you download the file and it's already in there. Then you just go across to Insert, and you'll see just below this bunch of applications, there's an option for Insert Image. And then you choose which image. So I did a Mickey Mouse graph, for example, so I'll put that one in. And then I can just start putting all my functions to sit over the top of that one. That's how I got the nice name. I'm not particularly artistic, but that could have been a different image. It could have been a graph of or a picture rather of the Harbour Bridge, for example. All right, so that's one option. Another option is take the task to the next level. Maybe we want to insert a ramp. So we have a building that requires an access ramp, and now you can take it, pardon the pun, to the next level. So about that, folks. And decide, well, where would we put the axes? So you can decide perhaps put them along that pole, if that's where we're going to put the ramp. And then put your lines in where you want to do it and make sure that the lines meet the code. And then we can start taking a scale and see whereabouts would the ramp finish, start and finish, by looking at coordinates and applying them to the image. And then hopefully, once your work is done, you'll get something like that, a completed project that we know fits the requirements. This one would be a little bit harder because the ground's on a slope. So that could make the question a little bit more complicated. But there's no reason why kids can't be taking photographs and using it. There's plenty of opportunities in there for students in that regard. All right, so the next thing you're probably wondering about is how did I make, like in the Marge Simpson one, or the Lisa Simpson one rather, how did I make the objects appear and disappear? Well, let me show you. So I'm back to my graph application because that's where everything's being done today. And I want to make stuff appear and disappear. So I'm going to add some text. Now I can do menu, actions, and text that way. Or, because it's done quite a lot, you can just right-click if you're on your computer and just put text. And here I'm going to write quadrant 1. And obviously I'll put that in quadrant 1. The next thing I'm doing, here's a little tip for people that are watching today. If you press P, if you're using the CX2, that will give you an option for point or point by coordinates. So I'm going to do point by coordinates. And I'll make them 2, 4. So obviously my point is in the first quadrant. And what I want to do is I want the word quadrant to appear or disappear. So disappear when I go over here, or appear when I come in here. So how would I do that? I'm going to assign the X coordinate by right-clicking on it, and I'll click Store. XC for X coordinate will do. You can call it anything, but I'm just trying to keep it simple. And then I'll do the same over here. And I'll store that in YC. Now, what I do know is X has to be positive for it to be in quadrant 1. So let's start with that. I'll right-click on quadrant 1, and you'll see down the bottom it says conditions. So my conditions are when XC is greater than 0. That's when it's going to show me the words quadrant 1. So if I move over here, it disappears because the value for XC is no longer positive. So it appears or disappears based on where my cursor is, well, where the point is. The only problem is it's still there, and that's not quadrant 1. So let me go back. I'll right-click on quadrant 1, click on conditions, and there's another condition I need to meet. So, and Y coordinate is greater than 0. Now, if I move it across, disappears. If I move it down, disappears. So let's try another one, quadrant 2. So in quadrant 2, again, we look at conditions, and obviously we want XC is less than 0, and it's literally the word and, YC is greater than 0. So now as I move across here, we can see we're in quadrant 2, quadrant 1, and away we go. So you can make text appear, or you can make graphs appear and disappear depending on where you are. It's exactly the same thing. So if I put a function in, I could make this function disappear depending on some value for this coordinate. So I could say conditions, show when x is greater than 1. I don't know why, but just because I can. So my graph will appear and disappear. So that's how you make stuff, and that's how I made all those graphs disappear as I wanted to them. I just made them dependent on some slider. So we're now up to our next opportunity for people to answer questions. My question is, where am I? Now, I'm not speaking literally right now. The image that's on your screen, if you know where it is based on those two black bars, be sure to put it in the chat. So we have options for easy questions, Brian, or hard questions. So let's ask people in the chat, do you want an easy question or a hard question? Just type in the chat whether you want easy or hard, and we'll take the first couple of answers. Whether someone, oh, that's you, Brian, easy or hard. Just give people a minute to type it in the chat.
Well, the first couple in is looking for easy. Might be too late in the day, Peter. Oh, I've got a couple of hard.
It might be.
It's yeah. Look, it's probably the next vote. We'll get it, I'd say.
Okay. Well, let's hang on. Let's do an easy one, then we'll do a hard one. We'll alternate between the two so they understand. They might have thought they want an easy one because they don't want to work too hard, like you said. So here's one of the easy ones. Let's try the first one. What is the product of the first 4 prime numbers? So what do you think, Brian? What do you think the 4 prime numbers might be?
Well, I'm going with
including 2.
Yep, I'm going with 2, 3, 5, 7.
Yep, 2 5s are 10. Yep.
Yep. And 10 by, I'd probably think 210. Yeah,
I think
a few.
I think I typed in 70. I missed one because I know what my answer was. So it shouldn't have been the first 4. What would it have been then? 2, 3, 5. I was only the first 3. Let me change the question. I can change it because I'm allowed to. Yeah. Well, it's not even the first 3 though. Oh,
that's not going to work.
Never mind.
That's not going to work.
Okay. What's the product of 2, 3, and 5? 2, 5, and 7. That would work. All right. I'm going to change it for this file before I put it up online. So you can see that's not very helpful, is it? It's really not helpful. Let's just take my next question. Ian has asked for another easy one. No, let's not. So let's have a look at some of the harder ones then.
Okay.
Yeah, that's right. I'm pretty sure I got the hard ones correct. Let's have a look at a harder question. What is the product of the first pair of odd successive prime numbers? And we're assuming 2 is not part of that family of successive primes. Let's see if someone can throw an answer out in the chat for us. Successive primes. Obviously what I'm doing here is just using this for a bit of revision and just for a bit of fun. That you can type your own sort of revision questions in here. And what I've done is a combination of 2 things. One, I've inserted a picture in the background, but then in the foreground, I've just added shapes. And what happens is I can make the shape disappear, like we saw before, based on a condition. Oh, someone's answer, 15. Let's try it, 15. Let's go back to our image. He is correct. It was that Ian again. Ian's doing well. Now, Ian, do you know where I am based on the small amount of information that's being revealed to you so far? So essentially what happens is any one of that you can see if I move my mouse around, it says polygon, and I could cheat. I could look at the conditions and see what the conditions are for the polygon. I hid some of them so you can't see them all. Otherwise, you would have just seen the answer anyway. So let's try another hard question and see if someone can figure out where we are. All right.
Well, someone's put a guess that agrees with me. Someone just typed in a guess that which was along the lines of what I was thinking, so it could be.
Oh, I'm impressed. Let us have a look at this one. How many factors does this number have? 2 squared by 3 squared by 5 cubed. Now, there's a really cool activity on the website, which is called Factors That Count. And what that does is gets the students to investigate the prime factorization of a number, and they look at the patterns between the prime factorization and the quantity of factors that a number has. And ultimately, we come up with, if you add 1 to each exponent and then multiply that result, so it'd be 3 by 3 by 4. So I've added 1 to each exponent, 3, 3, 4. So what's that give us? 36. Hopefully I'm right this time. 36. See if it reveals any more of the puzzle. It does. It does indeed reveal more of our puzzle as to where we might be. Anyone like to have it as a guess? Let's see if I'll do one more. This factor density, I kind of like this one. What is the number with the highest factor density? That means if I get the number and divide it by how many factors, I get some idea of its density. Well, 12 is the answer for that one. And maybe we're getting an idea on where we are. So again, just to show teachers, all I've done here, I've inserted a picture, family photograph. There's a bit of a clue here. It says magic, K-I-N, and it was on the news just recently as well. But essentially what I've done is I've just put these polygons on here, and if I right-click on that and have a look at the conditions, you'll see it says when I is either less than 256 or greater than 256. I could write when I is not equal to 256, show the polygon. In other words, it's going to be hidden if I type in I as 256. So let's go to where I is. Oh, that's an interesting one. It's probably down here. Oh, L, sorry, L, not I. So let's try 256. And there we see a bit more of it says Magic Kingdom. So the harder questions reveal, obviously, the better clues. Now, that was taken from a game show that used to be, Disneyland. Very good, Brian. Impressed. Did the word Magic Kingdom give it away, or was it the news story that gave it away?
No, it was the tower in the centre. I reckon I recognised that. Yeah.
Yep. And, of course, it just reopened after, 12 months or so. Yeah. So, yeah, that's a combination of what we've done so far. Picture in the background and just putting a bunch of... And they don't have to be regular polygons here. You can create all sorts of weird shapes there and just layer them one over the top of the other. Some people do it with PowerPoint. I thought it was kind of cool that I could do it here because then we're going to have mathematical questions. And when they get the mathematical question right, it reveals a piece of the puzzle. So that's conditional formatting in your graph area. All right. Here's one for people to think about. What on earth is that trying to talk about? I kind of like that. I saw that as a piece of humour on the web somewhere. I thought, I like it. We have a stapler and we have a staple remover, something that undoes putting in staples. So it's kind of a really bad math joke for inverse functions, right? So what I thought I'd do there is show you how we can do inverse functions. Now, this was actually a question asked to me very recently, actually this morning, someone was asking after it. So let's put something in like y equals x squared. Now, if I want to do the inverse, we talk to students about swapping the x and y. So I've written y equals x squared. So let's change the function type to relation. Now my function is in f1, so I can say x equals f1 of, x. What did I do wrong there? X, that would be a y, it's better. So now I've got my inverse. Probably more meaningful if I go ahead and do something like this. Well, actually, I'll leave it under relation because I can type y equals x. So we can kind of see that we have a reflection in the line y equals x. Now, that's not cool enough because I just typed the primitive function in here, y equals x squared. That means, now, before I drag it, I've put the cursor really close to the turning point, but it wants to move this relation plot 2. But you'll notice to the right of that it says tab. I press the tab key. It says, do you want to move relation 1? No. press tab again. So it's just cycling through all the objects that are there. Graph 1 is what I want to move, so I'll move it over there. So that's really cool, that the dynamic nature of our graph area means that our inverse is also dynamic, which leads us on to our next question. If I've got a parabola, I want to know how many solutions are possible whereby the original function intersects its inverse. So I'm thinking there might be 0, 1, 2, 3, or 4 points of intersection. I'm also thinking that maybe one of those is not possible. So let's go, see if people can guess which one of those is not possible for the number of points of intersection between f of x and its inverse when f of x is a parabola. Well, we've kind of given the game away in the first one, haven't we? Obviously, 0 points of intersection is the case here. So let's move it around a little bit. And I'm thinking that one kind of becomes obvious, that the two graphs are just touching. They're a tangent to the line y equals x. So there's exactly 1 point of intersection. So we can cross off 0, because that's possible. We can cross off 1, that's possible. Let's move it around a bit more. Again, you can see it saying plot relation to. I don't want that one. That's the one I want. Now, here's another good one. So I've got point of intersection on the line y equals x and another one on the line y equals x. Now I've got a point of intersection over here, and obviously it's reflected point over here. So that's 4 points of intersection I can count there. So 0 is possible, 1's possible, and 4 is possible, but we haven't got a 2 or a 3. And I'm just going to leave it about there somewhere. Oh, that's too far over. Let's try again. We can also, of course, do this. We can dilate. So I'm going to leave it to the punters, to our participants, to work it out later on and see if they can figure out, is it possible to have 3 points of intersection or 2 points of intersection? Those two options possible. Now, of course, you can do it visually, but then you'd also need to think about it mathematically. Mathematically, what's happening if there's 2? Mathematically, what would have to happen if there's 3? Now, that's not the only way we can do an inverse. So I'm going to put another graph application in here. And this time I'm going to put in the line y equals x, done that one. And I can't reflect a point in that, so we can use transformations such as reflections because it's a geometry space as well. But I can if it's drawn geometrically. I know that sounds a bit weird, but let me just draw a line over the top. This is a critical step in this one. So I'll draw a line going from there to there. And because it's a line, not a segment, it goes on forever. I don't need the little handles on my line, so I'm just hiding them because I like it neat. And now I'm going to type in my function. Just something simple. Move it over there. I'm going to change its color. And now I'm going to put a point on there. Oh, actually, before I put a point on there, let's just go point. And we can get its coordinates. Here's its coordinates. And then, to move the point around, coordinates update. But the geometry tool says transformation to a reflection of that point in that line. So now I can get its coordinates. And we can see, let me put those two together. And you might want to color code them to help the students. You can change the number of decimal places being displayed if there's too much information going on there. But I think students pick up pretty quickly that the x-coordinate of this one seems to be sitting over there, and the y-coordinate seems to be sitting over there. They seem to have swapped around. So let me just delete that. Obviously, its reflection disappears. But now, press P, point, and I can put a point on my function. Now I can reflect it. Because I put my point on the function, it's going to stay on there. It's kind of trapped. So I'll go to Geometry, Transformation, Reflection. Reflect this point in this line. And now my reflected point will always move in a path defined as it's in relation to the curve that it's sitting on. Now, of course, we can do things like this. We could do a trace. I could do a geometry trace, which means it'll leave a series of points, or you can also do something called a locus. What's that under construction? Locus. A locus of this point there. And just like I'll call it the algebraic way to do it, this geometrical way to do it, our locus is also dynamic. So that's doing inverse functions, but I've got one more up my sleeve for inverse functions. This one at a higher level. I'm going to insert, just so I don't mess it up with the stuff that's there, I'm going to insert a new problem so I don't catch any of the variables that I might have used before. All right, another little trick. This one we're going to do is for specialist maths, sin x. Now, I would like to restrict the domain of that by placing points on it. So let me try that. Put a point on here and over here. And I'm going to store that one in A. And I'll store this one in B. Now, I'd like to restrict the domain of this function to go between A and B, but that would give me a circular definition. That is, you can't determine its domain, because if I put the point outside what it says, it's kind of trying to figure out where it's at. It doesn't work. You can try it. So what I'm going to do instead, I'm going to say sin x, given A less than or equal to X less than or equal to B. So now you'll see my second graph, the red one, is in fact got a dynamic domain. So I can either hide this one or change its attributes to, I guess, de-emphasize it. And now I've got what looks like a dynamic domain for sin x. And of course, if you're thinking specialist maths, hopefully you're figuring out where this is already going. And that is, I want to look at its inverse. So let's just put a line in here. And if I want to reflect it, I can do F2, because if you have a look, the graph that I'm interested in, the one that has the domain restriction on it, is F2. Now, you can either do it using the reflection process we did before, that geometrical space, or let's have a go at the first option we had, which was relation. And so we're saying that x equals F2 of x, I did that again, of y. So now as I move my restrictions here, you'll see that the reflected function, our inverse, also changes. So now, of course, we can say to students, well, how would you restrict the domain of this function so that the inverse is a one-to-one function? If I put it there and there, we can see our inverse is not a function. I can put it there, but then there's values that I haven't collected, so I could put it back to there, and that seems to work quite nicely. If I go past that maximum, then I'm coming back on myself. So it seems reasonable to put it between the minimum there and the maximum there, which of course we know is negative pi on 2 and pi on 2. And so we can think about the inverse function and what its domain might be. And you can put points on the end there as well and get their coordinates, but kids can swap them around here. Now, the beauty of all of that is if I go back to my original functions, so I'll go back to this one, sin x. The problem is now I've got to change it in 2 spots. So I'm going to change it here and call it f1 of x. Still works, but now the beauty of it is, if I wanted to change my diagram and say, let's have a look at the domain of cos x and its inverse. And now I can move to there and to there. So now students can see why the domain restriction applies to cos x to get its inverse. And of course, you can do the same thing for tan x. So that's some cool features about the inverse and using some dynamic stuff. All right, how much time we've got left? 20 minutes. We've got a bit of time. All right, next. Whoa. Here's a tough question, Brian. Did I mention we're doing this one?
Yeah.
Find the equation. Yeah, find the equation of the locus formed by the intersection of the altitudes of a triangle with vertices on the function y equals 1 on x. This is one of my all-time favorite questions.
Yeah.
Now, in part, it's because most students throw their hands up and have no clues. But the mathematics is applicable, believe it or not, to Year 11. There's nothing on that a Year 11 student cannot do. Well, it's not so they can't do the question, but what I'm saying is that the mathematics that underpins the answer is all within the Year 11 maths course. And the point here is that we can intermix geometry and graphs in the graphing environment. So we're going to have some more fun with our graphs. Let's do it. Let's get rid of that one. And we'll create a new. Now we'll create a graph. So the first thing we've got is fairly obvious. We can graph our function. And the next part of the question said, we want to find altitudes of a triangle. Where's the triangle? The triangle has vertices on this function. So I'm kind of working backwards through my question. You can also change the scale a bit. Let's go menu and geometry and shapes, triangle. So it says the vertices have to be on the function. So I shall do that. And as you'll see, I can try and drag them off, but they're not budging. They're stuck on our function. So I've satisfied part of the conditions to this question. That is, I have this function, and I've drawn a triangle so that its vertices are on that function. The next thing is this thing about intersection of altitudes. So students might need a refresher on what an altitude is. You can do like what I used to do, draw a really simple triangular shaped mountain and then show them an altitude which is not perpendicular to the ground, and the kids soon come back with, oh yes, it's got to pass through the top of the mountain and it's got to be at right angles to the ground, i.e. geometry, construction, a perpendicular line. So perpendicular to the ground and through the top of the mountain. Perpendicular to the ground and through the top of the mountain, and perpendicular to the ground and through the top of the mountain. I'm going to change the attributes so we can see them a bit easier. I'm just using a right mouse click. And on the handheld, of course, that's control and menu, if you're using the handheld to do these. And there we have the intersection of the altitudes. It's not trivial, of course, that the altitudes actually intersect. But what's super cool is where they intersect. Let's just track them. Geometry, intersection of this altitude and that one. That altitude and that one. They're intersecting on the function. The locus is the path that it's following. Let's see what happens if I put all three points on one branch of our hyperbola. Look at that. Still intersecting. Let's put two of them over there. We'll put all three over there. And we're still getting the intersection altitudes to be on the function. And the mathematics to do that is actually very easy. So when you finish this, if you're not hungry yet, try doing the maths for it. It's actually pretty straightforward. And there's lots of other things you can do, like what happens if we change that to y equals x squared? Does it still work? Well, that's how hard it is to do. And if it doesn't trace out the function, I wonder what function it does trace. And of course, kids can use their algebra to work out the equation to the line that that's tracing out now. And what about other functions? What about something like a parabola? And you can go and explore. What about the other centers of a triangle? You've got a whole investigation. That's blending geometry with your graphs. All right, that was that question. We have another one. What happens when, we raise an imaginary number to a higher and higher power? Oh, now with the inverse ones, by the way, folks, is we just released what we call a short focused investigation on functions and their inverses. And the function y equals 1 on x is a really good one to include when you're looking at inverses, about how many points of intersection you might have. And there's some other ones in there that help get rid of some of the misconceptions around functions and their inverses. So good one to check out. It's for math methods.
Yeah, Foxy, I know that was mentioned in a newsletter that went out this week, I think. I'm just going to, while you're working on this problem, I'm going to see if I can find it in our on the web page, and I'll put the link in the chat.
And put the link. Nice work. Thanks, Brian. All right, so let's have a look at this one. What happens when we raise an imaginary number to a higher and higher power? Well, we do actually have the Argand plane. It's just a little bit in disguise. So let's have a look. It's in here. Nope. Let's just start a new document. We've got plenty of them. So to start off with, I've got a calculator application. I'm just going to say Z is equal to A plus B times, and here's another little shortcut tip for folks today. If you press the pi button, that's where your imaginary number is. Press it again, and you can see it just keeps on scrolling across as I keep pressing it. So double tap on it, press enter, and it's just safe trying to use the arrow key to get across. Just double tap. All right, so I've defined Z equal to A plus B times I. So what? Well, now let's put our graph application in. Control I. It's a nice way to insert that. And P, just pressing the button P will allow me to do a point. And I'll put one in with coordinates. I'll go 2, 3. So I have this point with coordinates 2, 3. And you saw it before. I'll right click on it and I'll store that in A. And I'll store this one in B. So there's my imaginary number. Doesn't look very imaginary. It is now. Here we go. Now I have the Argand plane. It's all good. Renamed it. So this is our imaginary number Z. And of course we could measure the magnitude of it. We can do all sorts of things. But the question was, what happens if you raise Z to higher and higher powers? Well, for that, I'm going to insert a spreadsheet. And I'll call this, let me think, ZX will do. And I'll call this ZY. You can call it whatever you like, just something meaningful. And here I'll type in equals real Z. And you can see it's just returning what is actually the value of A, which is fine. And in here, I'll say that's equal to imaginary part of Z, and we're done. And over here, I'm going to put in, let's say, a 1, and I'll 2, and so on. So here I want to do Z squared. Now, I could have typed in Z squared here, but you'll see where this is heading. So what I want to do is equal to the real part of Z raised to the power of 2. Well, 2 is over here in cell C2. And here equals the imaginary part of z raised to the power of c2. So I can plot zx and zy as a scatter plot. Won't be very exciting yet. I'm just going to move that in because otherwise you're not going to see it. So now we'll go Menu, Graph, Scatter Plot. And remembering we have zx and zy. So now we've got 2 points in our scatter plot. And you see it kind of wanders around depending on where I put z. Z squared could be right on top of it. Wonder where else it could be right on top of it. Not there. Not there. It's kind of cool. But what about z cubed and z to the 4? So I could continue adding numbers in here, but I'm going to do something a little bit sneaky. In here, I'm going to put in what we call a slider. Insert slider. I'll call it n, and we'll make n go from 1 to 20. Should be enough in steps of 1. I'll minimize it, and I don't need a scale. And let's just put him up there. Now, what I want to do is increase the size of the scatter plot when I just start clicking here. I want to see more points appearing. So I can do that nicely in here. I can say equals sequence x comma x. X is my variable, x is the formula. I'll start at 1 and I'll go through to n. Yeah, I want to overwrite. And it's a variable. So you can see it's gone 1, 2, 3, 4 here. So if I change that to 5, it's now created a list that's 5 units long. If I bring it back, it's now just 3 units long. So now, because I've told it to raise it to the power of whatever number's in here, I can just fill down. Now, I think I said about 10 or 15. So let's just do data, fill. 15 will do. And so it's not calculating anything here because there's nothing in column C. But now, I can start to add them. You can see it's starting to curl around, which is kind of cool. And I can grab that point, and they're all being recalculated. So you're getting this kind of spiral thing. The spiral thing is going to look better if I connect the scatter plot. So let's do attributes, and we'll connect the points. I might want to see a few more. And the other thing you got to watch is sometimes you got to grab the scatter plot. You got to grab the point. And some nice pictures in here. Kind of looks cool. You see there, I've grabbed the scatter plot there. Yeah, and some kind of weird numbers happening in here. I might want to zoom out a little bit. And I'm going to change, oops. I'll use the window to be easier. Window, settings. Let's go scale of 1. The other thing I might do on here is, let's just view a grid. Might be helpful. So, if you know where this is heading, you can see if the magnitude of my value for Z is relatively small, we kind of spiral in. If I pop on the outside there, we sort of spiral out. That's kind of cool. Now, if I put it over here, we have a magnitude bigger than 1, so we've kind of spiraled out. Put it in here. So perhaps a circle in here might be useful. A circle of radius 1, you already know how to use the geometry tools and do that. Now, we've only got a couple of minutes left. So there's another activity that was released this week, which was complex spirals. And it does this, but it does some extra. Now, I'm not going to do the complex spirals one. I'm going to talk about one called imaginary explosions. It does something slightly different. So in the one that we released this week, it actually looks at partial sums. So what happens when you start adding these sorts of things up, Z1, Z2, Z3, where Z1 is Z to the power of 1, Z2 being Z squared, and so on. But imaginary explosions does something different. Let's have a look. This is the document that's available to you for imaginary explosions, and it says each time you raise it to a new power, just add another value. So you add D, some point. some imaginary number. So you square your original imaginary number, and then you just add another one to it. So here it is here, and here's the value that I'm adding. Oh no, that's the Z. Sorry, there's the Z value. We get something similar. Let's go back to what we had before. Let's imagine Z is about 0. There it is, 0, 0. So this is what we kind of had before. But then, hang on, let me just check this. No, I tell a lie. It's the wrong way around. This is the value that we're squaring, and this is the value that I'm adding. So now if I put that to 0, this is the thing that we had before. I want to stay inside 1, otherwise it kind of spirals out of control. So you get the pretty pictures that we had before. But now, if we go and add some other value, some other Z, my magnitude here is less than 1, but now it's kind of spiraled out. Spiraled back in. You can see it's got this funny little curve into it. Now it's spiraled out again. And sometimes I go outside and it will spiral in. Even though I'm outside, I have an absolute value bigger than 1, and it can spiral back in. It's almost random where it spirals in and spirals out. So here it's spiraling in, so converging, converging on some value, converging on some value, very definitely converging. Oh, all of a sudden I jumped out. So we go from here to here, and it's gone out. Now, if you kept a record of where it spirals in and spirals out and coloured them in different colours, so let's say red was spiralling out and black was spiralling in, you get a lovely picture of the Mandelbrot set. So I don't think we can have any more fun with graphs than creating a Mandelbrot set and just doing some really simple square it and add a value, square it, add a value. And that's all I've done down here. You see it in the formula bar, square our value for Z and add some ZC, ZI, which is the coordinates, probably that point there. We'll see them down here, ZX, ZY, and ZC, and ZI. So that's all I've done, is just given these points some coordinates, done some calculations in a spreadsheet. And that's about all I've got time for. So, unless anybody has any questions, I think we're just about done for the day, Brian.
Okay, thank you, Peter. I shall just play the closing credits. Once again, an opportunity to type in any remaining questions that you might have of Peter into the text as we go. I'm just putting in a plug also for our next webinar event, which will be on the Tuesday, the 1st of June at 4 p.m. And that's middle school mayhem. Obviously, we've gone into a little bit of our special maths topics here. But if you've got middle school classes as well and looking for some activities there, what we've got in that one is a panel. We'll have a panel of presenters sharing their favourite or some of their favourite ideas. I'll be one of them, and I think you are too, are you, Peter?
I reckon there's a fair chance I'll be in there.
Very good. Okay, so I shall take us back across to my little closing PowerPoint slides here, which also gives you details of where you can find a copy of the recording for this event and where you can download activities and the like. Just one question that I had, Peter, while I'm swapping to that. We did have, when you presented the Argand screen, sorry, the Argand plane, one of our participants typed in that the vertical axis. Now, is that real or imaginary?
The vertical one, I made it imaginary.
Yes,
the horizontal one, I made it real.
And I agree with you that the vertical axis is generally imaginary, but he was convinced that he could see it.
Oh, I could have hidden it, I guess.
And then he would have to imagine
Very
it.
good. Yeah. Well,
thank you, Ray,
like
from Melbourne for that comment. Yeah.
Oh, was it? All right. Well, I've got one for Ray then. There was two Polish bank robbers, and they were heading out towards the airport for their getaway, and they were being hotly pursued by the police. And they decided they'd just crash through the fence of the airport and barreled on out onto the runway and charged onto a plane and jumped into the cockpit of this little plane. And the police were bearing down on them, and the guy says, "Come on, Meg, hurry up, we're going to get this plane in the air." And he said, "Shut up, I'm just a simple pole in a complex plane."
Yeah, okay.
We can edit that one out.
So I think on that note then, Peter, thank you very much. It is probably a good time to then conclude this event. We hope it has been beneficial to you. Remember, you can watch the recording, you can download all of the activities. That web page that Peter maintains, full of excellent activities, all for free. Student worksheets and marking guides for teachers. And remember, our next webinar event, 4 p.m, be on a Tuesday, the 1st of June, and that'll be Middle School Mayhem. Thank you for joining us.
Did you put the phone number up there before, Brian? Because I had someone ring me the other day, and they said when they got through, it said, "I'm sorry, the number you have rung is imaginary. Please rotate your phone by 90 degrees."
Okay. Fair enough. Okay. Good evening to all.
Thanks, Brian.
Bye.